Okay, good morning, class. Okay, can you please take the attendance?
Okay, sir.
Right, thank you. Okay, so we continue our previous from our previous lesson, right? So I think I stopped until here, right? So I think I stopped until here. Is it correct? Can someone please check?
Yes, sir.
Yeah, okay. So we continue, right? Actually, this one we still on the gravitational force. Okay, how to calculate the gravitational force. So this one is actually if you want to calculate the gravitational force between the Earth and also the Sun. Okay, so as example for this one, okay, so you already know the mass of the Earth is 5.97 times 10 power of 24, and the mass of the sun is 7.35 times 10 power of 22. Okay, so just multiply and you just multiply with the gravitational constant, that is 6.67 times 10 power of negative 11. Okay, and then the radius. So the radius is from the radius of the earth and the radius of the sun. So already given you the r is 1.5 times 10 power of 11, then you square it. So this one we get 1.30 times 10 over 15 Newton. Okay. Right. For this one is actually the gravitational force between the Earth and the Moon is 2 times 10 power of 20. So what is the distance? Right. So this one I want you to try to calculate. Right. So can you try to calculate the gravitational, sorry, the distance between the center of the Earth and the center of the Moon? So I give you the value of G here. That is 6.67 times 10 power of negative 11. And the mass of the Earth is 5.97 times 10 power of 24. This is for the Earth. And the mass of the Moon, I find in the previous slide. Mass of the Moon is, do we have it? No, I found the mass of the Moon. Mm. 7.35 times 10 power of 22. Okay. Okay. So now it already give you the F, the value of F, okay, and already give you the value of the mass of the Earth and also mass of the Moon. So you need to find the R square here. Oh, thank you, Viken. So if I substitute the value, K and G is 6.67 times 10 power of negative 11. The mass is 5.97 times 10 power of 24. And the mass of the moon is 7.35 times 10 power of 22. Okay, so we divide, okay, with r squared. That one need to find the r, the radius. 3.83 times 10 power of 8. Any other answer? 3.83 times 10 power of 8. So let's see whether it's correct or not. Okay, so you just multiply 6.67 exponent negative 11 times 4.97 exponent 24 times 7.35 exponent 22. Right? So this one is divide. So when you change to here, it will become multiply. So this one we go here will become divide, right? So 2 divide by 2 exponent 20. So we get, then we have to square root, right? Square root the answer. Yeah, so you got 3.83 times 10 power of 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so correct, 3.83 times 10 power of 8. Okay, so that's all for the gravitational force. Okay, so now, okay, we have to relate, right, the gravitational acceleration G on the surface of the Earth with the universal gravitational constant G. Okay, so means the value of the gravitational acceleration G means you already know the value of the gravitational acceleration on the Earth is 9.81, right? So now we are trying to relate, okay, the value of G on the Earth and also the value of the capital letter G for the universal gravitational constant G. Okay, so what is the relationship? Okay, so according to Newton's second law of motion, so what does the Newton's second law of motion state? So anyone still remember? What is the Newton's second law? Newton's first law is inertia, right? Okay, the tendency of an object, okay, to resist any changes, okay, in motion, whether it's still moving, whether it's still move in a straight line or whether it's at a stationary state. So that is the first law of Newton, that is inertia. So the second law, what is the second law of the Newton's second law? Anyone? F is equals to ma. So what if you want to put in the words, right? So that one is a formula. So let's say the question asks you state the Newton's second law. So how should you answer that question? You cannot give the formula F is equals to ma. Okay? And they ask you to state the Newton's second law. Anyone want to try? We can who is still not here. Force is directly proportional to the mass and the acceleration. No? Strong saja. Force is a product of mass and acceleration. No? A force to be equal to the change in momentum. Partly part of your answer is correct. Eugene and Nirupa. Are there in the maths class before? And when I put in the groups, in the parents group. Okay, so rate of change or momentum. Okay, so what does Newton's second law state? Newton's second law state that the force is directly proportional to the rate of change of momentum, right? So that is the meaning of the Newton's second law. Okay, rate of change of momentum. Okay, you need just to put F is directly proportional to the rate of change of momentum. Okay, because mv minus mu, right? Before this, you already know the F is ma. This is F is ma, right? This is for the equation for the Newton's second law. Then we derive that A is V minus U divided by T. And then we got mv minus mu divided by T. Okay, so that's why force is directly proportional to the rate of change of momentum. Okay, because this is the momentum, you already know this is the formula for the momentum. Okay, so what's the difference between mv and mu? The mv, they use the final velocity, and mu is they're using the initial velocity. So it's just like the initial momentum. Okay, and this is the final momentum. So final momentum minus with the initial momentum means there is a change of momentum. Then when you derive when you divide with the time, so it becomes the rate of change of momentum. Okay, so force is directly proportional to the rate of change of momentum. Okay, so can someone tell me rate of change of momentum is the meaning of what? Rate of change of momentum is the meaning of, there's a one physical quantity that using the meaning of rate of change of momentum. Yes, very good, Sajid. So impulsive force. So impulsive force is rate of change of momentum. Okay, very good. So according to the Newton's second law of motion, gravitational force can be expressed as F is equals to mg. So why g? Why not a? So actually a is very it's a actually as acceleration of an object, but the one g is a constant value, right? So the g is 9.8, so F is equals to mg. So that one is derived from the Newton's second law. So anyone can tell me what else that can we calculate by using the formula of mg? What are the other physical quantity, okay, that using the mg as the formula? Start with it's the last topic for chapter 2. Yes, very good. Weight, right? Weight is actually using this formula mg, and the unit is Newton. Okay, very good. So according to the Newton's second law of motion, gravitational force can be expressed as F is equals to mg. So from Newton universal law of gravitation, the gravitational force is F is equal to g m1 m2 divided by r squared. So what is the relationship between g and g? Okay. So this is the formula for the Newton's second law. So for this one, the force is actually equal. Okay. So if the F, both F is equal, we can just put that mg is actually equals to gm m over r squared. Okay. This one is actually to differentiate, right? So one use the capital letter M, and another one use the small capital letter M, is just to differentiate that there is two objects there. Okay. So this is, then you just equalize these two formula. Okay, so mg is gm over r squared. So this means the same object, so you can just cut off the m. Okay, so it will become like this. So the gravitational acceleration So the formula for the gravitational acceleration is gm over r square. Okay, so this is the formula to calculate the gravitational acceleration, right? So the next one, okay, so from here we can derive that when g is directly proportional to the g. Okay, so means the gravitational acceleration is, let's say this one increase, the value of the gravitational acceleration increase, so this one also should be increased. Okay, right? So that's the relationship between g and g. Okay, so what is the relationship? So this one I already answered. So this is directly proportional. Okay. So what are the factors that influence the value of the gravitational acceleration? So let's say when the question asks you the factors, so you just refer back to the formula. Okay. So what is the formula just now? G M, right, with R square. Okay. So this one you already know this is constant, right? 6.67 times 10 power of negative 11. That one is constant. So there is no change on the value of G. Okay. So the one that can change is actually the mass and the radius. So what is the factors that we influence? That is actually the mass of an object and also the distance of the object. So this will affect the value of G. This one is constant, so it will not change. Because this one is using, the value of G is actually can be used in the universe. The whole universe can use the value of G, this one, right? So mass of an object and distance of the object. Okay, so the gravitational acceleration always towards the center of the earth. Okay, so and this one I think you already know. So each planet in this universe has its own different gravitational force. Alright, so usually let's say at the earth, right, actually at the moon. So at the moon usually the gravitational acceleration is 1/6, okay, from our gravitational acceleration from the earth. So you just, let's say you just multiply, so you will get the gravitational acceleration for the moon. Okay, it's 1/6 from the earth. Okay, so the value of G, so this one is actually 10 is using for KBSM, but for you KSSM, we didn't use the value, or the G is 10 anymore. We use it as 9.81. Okay, so this one you have to change. Okay, this is the old syllabus. Okay, for yours we using 9.81 now. Okay, so please change, right? Change the notes there. Okay, so for example, activity 5, okay, so they're giving you the mass of the earth, right, the radius of the earth, okay, 6.37, and also the gravitational constant. So they ask you to calculate the gravitational acceleration for the 5 distance. So let's say I calculate at R, okay. So if you calculate at R using this formula, right? Remember, don't use this one. This one is gravitational force. Okay, so don't be confused. This one is a gravitational force. This one is a gravitational acceleration. So this one we use this formula, right? So the G here is 6.67 times 10 power of negative 11. The mass of the earth is 5.97 times 10 times 10 power of 24, and then we divide with the radius, okay, 6.37 times 10 power of 6, okay, and then don't forget to square it. Okay, so can someone try to calculate for me what's the answer for this one? So far, you understand? You want to ask teacher anything? Nine point 81. Okay, So 9.81 is actually correct because this one, the object is on the surface of the earth. So any object that actually on the surface of the earth is 9.81. Okay, it follows the gravitational acceleration. Okay, so that one we already know. So let's say any object that on the surface of the earth, the gravitational acceleration should be 9.81. Okay, then so let's say after that, okay, the object, right? The object travel to the outer space. Okay, so it move with the value, with the distance of the earth to the place, to the outer space that the object go. Okay, is 2r now. So the distance now is 2r. So 2r means you just multiply the 6.37 with 2. Okay, so let's try to answer. Okay, 6.67 times 10 power of negative 11, 5.97 times 10 power of 24. Okay, but the r is 2r, right? So 2 times 6.67 times, 6.37, not 27, 6.27, 6.37 times 10 power of 6. So this one you have to square root. So what's the answer that we will get? 4.91. Okay. How comes Avinash? You got only 4.91. We can the 8.07. Why so your gravity is... Calculate again, we can. Okay. Tava, is it Tava is here? Tava, can you respond to me? Tava Raja? Tava Raja, wait, I see. Okay, Tava Raja, you have to go to the appointment for the klinik pendidikan jenjang. Okay. Okay, Raja, you have to go on. Wait, I find your name. Raja, you have to go on 11 June. Okay, 11 June. Okay, so please take note. 11 June, 3 p.m. Okay, Raja. And Tava, you have to go on 28 May. Okay, 28 May at 9:30 a.m. Okay, so you go to the klinik pergigian jenjang. Okay. And then maybe you can take the card at the office because they give you the appointment card, so go to take at the office, right? So, okay, so what's the answer? 2.45. So everyone got different answer. Right, so let's see which one is correct. Did you square the r? Sometimes you forgot to square the r. So that's why you got the different answer. 6, 7, exponent, negative 11, right? Times 5.97 exponent 24. Okay, and then we divide by Okay, we divide by 2 times the R is 6.3737 exponent 6. Okay, and then you have to square it. So I got 2.45. I got 2.45. Yes. 2.45. I don't know where I missed, teacher.
Dalam.
Check it again.
Ada? Ada surprise.
Huh?
Cikgu tengah tuition.
Wait, someone give me. Wait.
Nak ambil gambar.
Huh?
Cikgu tengah tuition.
Okay. Wait, someone give me a surprise gift. Wait. Wait for a moment. Okay, where is it?
Pergi ambil tu dan saya kemana?
Did anyone send me any gift? No, right? Happy Teachers Day. Okay. Yeah. Okay. Alright, sorry guys. Sorry. Okay. Okay, so the answer is 2.45. Okay. So you can check the before this how I calculate. Avinash, which part is your that you miss?
Oh, JNT.
Which part that you miss, Avinash? He accidentally put the 2 or 2R at outside. Oh, okay. Alright. Okay. Right, so actually, you can check your answer. Okay. Here. Alright, so the answer is actually 2.45. Okay, so I just use r and 2r to calculate, so you can see from when the radius is increasing, right? So the radius is increasing, you can see the gravitational acceleration also will be decreased. Okay, so it will be decreased, right? So if you see in the diagram here, so from r to 5r, okay, the value of g will be decreased. Okay. Okay, so what is the value of the gravitational acceleration on the Earth's surface? So 9.8. Okay, so this is the value of the gravitational acceleration. If you see in the graph. So actually, this one is the graph for G against R. So this is the radius. So from here, from 0 until R, okay, from 0 until R is actually the object is still on the Earth. Okay, so when the object is still on the earth, okay, so when the radius increasing, the gravitational acceleration also will be decreased. Okay, this one the relationship is directly proportional. Okay, so just now we already calculate, right? So let's say from r to r, you can see the value of g is starting to decrease. Okay, and you already see the table just now, the value of each g. Okay, so it decreasing. Okay, so it's decreasing. So when it's decreased, so you can get this kind of graph. When you try to plot the value there, okay, so just now we plot the we just calculate the 2r, right? So you got the value 2.45. So the when you plot the graph, it is here. Okay, so if you want to calculate, you can calculate for 3r, 4r, and 5r. Then we try to underline the graph, you will get this kind of graph. So for this one, this is inversely proportional. Okay, inversely proportional. Okay, so from 0 to r, the object is on the earth. Okay, so it's on the earth. Okay, so it is directly proportional. So when from 2r to 5r, it is inversely proportional. Okay, so it is inversely proportional. So the r is decreasing. So this one is actually when the object is already at the outer space. It's not on the earth anymore. Okay. So this one you already plot the graph. So the graph shows the variation of the gravitational acceleration with the distance from the center of the earth. Okay, so from this part is directly proportional. Okay, from here to here is inversely proportional, the gravity. So means when the gravity is increasing, the radius is increasing. Okay, the value of r is increasing, the gravitational force will be decreased. Okay, so mean when you move further from the earth, the gravitational acceleration will decrease. So how does the value of the gravitational acceleration change when the distance from the center of the earth r is smaller than r? Okay, so it's directly proportional. This one I already explained. And this one, how does the value of the gravitational acceleration change when the distance from the center of the earth increase? Okay, so this one is inversely proportional. So teacher, when you go further from the earth, you won't get much gravity effect. That's why we'll be floating. Yes. Okay. So later, you will learn that about the microgravity. So that's why, because of the microgravity, so that's why you can see when the people, okay, in the spaceship, right, they are floating. Okay, the astronaut, right, they are floating. So that time we are weightless. Okay, we are weightless. So it's almost like our G is almost zero. So when our G is like almost zero, when you try to calculate the weight, right? So G is almost zero, right? So the weight is like there is no value, okay? There is no value of W here since the G is almost zero, okay? All right, for number 5, okay? So this one, try to calculate the value of G. Okay, so just use this formula. Make sure you calculate correctly, okay? put bracket because your calculator, okay, it doesn't know which one they need to calculate first. Oh. Oh. 9.81. Any other answer? Nine 9.81. So is it correct? Yes. 9.81 ms negative. So that is the gravitational acceleration on the Earth. Okay, so let's say for this one, a radar imaging satellite orbits around the Earth at the height of 480 kilometers. So what is the value of the gravitational acceleration at the position of the satellite? Okay, so this one you have to remember, okay, our R is only from here to here, right? But now the satellite is at the outer space here. So means you need to add something to the R here before you're using the formula, this formula. And remember, this one, change to meter. So remember the prefix, right? Remember I just do the revision. Okay, for chapter 1, the value of K. K is what? K is kilo. 8.49. Others? You should try to give answer, because I will take this. Right now, teacher filling your PVD, right? So I'm finding because in some of your notes are not complete. Okay, so I cannot give you like PVD like 3 like that only. Okay, because you're not complete your notes. Some of you lah not complete your notes. Sometimes your exercise also not complete, right? So this is the chance for you, right? I will take this also as a proof because you know that all the chat is also recording, right? So I have a copy of your chat. So your chat will be proof that I giving you this TP is actually this is what you should get. Okay, so mostly like BK, Saji, just give answer. I don't mind whether it's correct or not. At least you try. Rather than you just keep quiet. Okay? 8.49. Others? What's answer that you get? Same. Okay, so let's see whether it's correct or not. So 8.49. Correct. Okay, so this one you can see the R here, the R that we use is you have to add, okay, also with the distance of the satellites from the Earth. So that's why we add 4.8. So some of you might wonder how does it become 5.8. So I try to calculate again. So G is 6.67 times 10 power of negative 11. Okay, and the mass is 5.97 times 10 power of 24. Okay, so the radius. Okay, so the radius here. Okay, I already draw just now. Okay, so R is actually only from here, but the satellite is here, right? But they already give you the height of the satellite is 480 kilometers. So from here to here is 480 kilometers. So how does we change the 480 kilometer to the meter? So some of you maybe just multiply by 1000. Okay, but the correct way is actually kilo is 10 power of 3, right? So this one, if you change to the standard form, it will become 4.8 times 10 power of 2. Okay, so then you just add because it's a multiply, so the index you have to add the power here, right? So 4.8 times 10 power of 5. So that's how you get 4.8 times plus 10 times 10 power of 5. Okay, then after you add, you have to square it. So you get the answer 8.49. Okay, 8.49 ms power of 22. Okay, so discuss the condition where the value of the gravitational acceleration is almost zero. So this one I told you just now about the microgravity, right? So it's the condition where which people or object appear to be weightless. Okay, so the effect of the microgravity can be seen from the astronaut and objects flows in their spacecraft or spacewalk. So heavy objects move around easily. So you can see in the video, right? They are floating. So this one is the microgravity. Okay. So this is the condition that we call it as a microgravity. So next we move. Okay. So already just 1 minute. Okay. So I think I will start until here. Okay. And we continue tomorrow. Okay. Tomorrow is our class is 8:45, right? Is it correct? Yes. All right. So I stop until here first. So we continue this one on tomorrow. Okay. So thank you, class. All right. So I'll see you tomorrow. Okay. Take care.
Thank you, teacher.
Okay. Bye bye.
Thank you, teacher.
Thank you,
Okay.
teacher.
Bye.
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 Gotcha.